Okay, let's look at practice test 4, and let's see if we can work through some solutions here. Okay, question 1. The purchasing department for a regional supermarket chain is considering two sources for purchasing 10-pound bags of potatoes. A random sample of bags from two suppliers was measured, and the following descriptive statistics were determined. Okay, we have sample sizes, mean weights, and sample standard deviations for two samples. Perform a test of hypothesis that there is a difference in weights of the bags of potatoes supplied by the two vendors. How do we measure the weights? Well, we'll be measuring them in terms of the mean weight. So we're testing a difference of means. Okay, testing difference of means, that narrows us down to z-test or t-test. We do not know population standard deviations, so we have to use sample standard deviation. That makes it t-test, and there are two samples here that are independent. So this is a two-sample t-test. Okay, round to 5 decimal places. Now this one is built in. We'll see if this gives us the right number of decimal places we need. If not, we may have to do this without the shortcut here. Okay, but we can go to stat tests, and a two-sample t-test is number 4, and we're entering our data from statistics. X bar 1 is under A, 100 pounds, mean weight. Standard deviation sample of that sample is 0.6, and the N is, I'm sorry, I've got that wrong, N is 100. The X bar is 10.2. Okay. Alright. Now these are supposed to be 10-pound bags. They're a little heavier on average. X bar 2 is 10.4, a little heavier. Standard deviation 0.5, a little less standard deviation, and a smaller sample size of 75. And let's see, p-value of a test, we got to figure out if it's one-tailed, two-tailed. Difference, that there is a difference. That's mu1, or mu1 not equal to mu2, or the difference not equal to 0. So that's a two-tailed test, not equal. We'll just always, for us, we'll just leave that on no for pooled, and then calculate. And so this gives us our p-value, and it does give us plenty of digits there, so we can just plug that, we can type that in. Let's let me get here for a minute. See if I can get both the calculator and the computer to show up on the same screen. Okay, so you can see both of those. There we go, that's a little better. And it's 0.01738. Is that 5 places? Yes, it is. So that's our p-value right there. Degrees of freedom is based on some formula where it uses these two numbers together. We don't really need to worry about that. It will compute it for us. At the alpha 0.1 level, is there enough evidence to say that there is a difference in the weights? Well, let's see. Well, 0.1 for alpha. We got p is 0.017. So notice our p is less than alpha, so there is enough evidence to show that they're different. Okay, looks like that's all we have for that question, so let's go on to the next one. Okay, choose a single best response for each question below concerning concepts of hypothesis testing. Scroll down to see all the questions. Okay, number 1, in performing a two-tailed hypothesis test for means, the value of p, the p-value, represents, let's see, standardized value, sample mean, no. Probability of attaining particular sample mean. probability that the sample statistic would be further from the hypothesized mean than the sample mean, given that the alternative hypothesis is true. That's it right there. No, wrong. That's not it. That's it. The null hypothesis is true. So what we assume is that the null hypothesis is true, and given whatever distribution that's going to be, chi-square for variances, z for standardized normal, etc., wherever it is, we're further from that. And this says further because further could be further in one direction, one-tailed, or one-tailed the other direction, just left, just right, or it could be two-tailed direction. It could be further either left or right. So that's what we want. And in this case it's testing for means, so it'd be like a z distribution or a t distribution. When performing a test of hypothesis on the TI-84 and we select the draw option, the area that's shaded is actually a p-value, e. Okay, and we've looked at graphs before where we looked at the graph of the alpha area and we looked at graphs of the p area. Those graphs, those are based on the same curve but two different areas that are shaded, and the one that's drawn by the 84 is the p-value. So essentially the calculator uses the p-value approach. In the p-value approach, we reject the null hypothesis in favor of the alternative hypothesis when p is small, smaller than a. So if the p-value is very small, then the probability of making a type 1 error basically is going to be very, very small, and that's what we want to happen if we reject. In the classical approach, we reject the null hypothesis in favor of the alternative hypothesis when, okay, in the p-value approach, you're comparing p-values to alphas. In the classical approach, you're comparing critical values to test statistics. So the test statistic is try that again. The test statistic is further from the hypothesized value than the critical value. That's when we reject, and that's what it's asking for. So that's A. All right. Again, some multiple choices about competence. The point estimator for the parameter of interest is, actually, I know how this question is constructed, and it's asking for D, exactly the center of the confidence interval. But actually, that's only true when you're doing means and proportions. It is not necessarily true for variances. But I think, so this question really should be reworded. But D is the answer it's looking for. So if that one shows up on the test, just go ahead and answer D. The width of the confidence interval is twice the margin of error. Okay. Which of the following will make a confidence interval smaller in width, assuming no other changes are made? If you increase the confidence level, you're going to make the interval wider. If you increase the sample size, that's going to make it smaller. If you increase the margin of error, you make it wider. So the only one that makes it smaller is increasing sample size. Which of the following will increase the confidence level of a confidence interval, assuming no other changes are made? Decreasing sample size will increase the confidence. We're assuming the width is the same this time. Whereas last time, on this question up here, 3, we were assuming no other changes are made. So see, we're comparing width and, well, we're comparing width of the interval with some of these other things. Margin of error is twice the width, so increasing the margin of error increases the width. Sample size and width, then what we're doing there is we're assuming the confidence level was set fixed. So increasing the sample size makes the width smaller. And then when we're talking about confidence level, we're assuming the sample size is fixed. So the sample size is fixed. Increasing the confidence level will make the interval wider. All right, down here we're keeping, what are we keeping fixed? We're keeping, we're changing the confidence level. So when we're changing the mean, what does that do? Well, that moves the interval around, but it doesn't do anything about the width of the interval. And it doesn't really have anything to do with the confidence level at all. Increasing the margin of error means that we're increasing the width of the interval. If you increase the width, you will increase the confidence level, assuming you keep the sample size the same. So C will work. If you decrease the sample size, you're going to, and you keep the width the same, then you're going to decrease the confidence level. So we want to increase the confidence level. We want to increase the margin of error. Okay, so we got a study that is conducted, so some kind of journal, on whether the price of a journal is correlated with the quality. Several quantitative variables were recorded in each of the sample of 5 geography journals. Cost of a 1-year subscription, journal impact factor, the average number of times an article from the journal has been cited, number of citations, and a relative price index. And so we have some data there that we may want to get back to in a minute. Fit a straight line model, so this is a regression, linear regression, of cost Y to GIF X. So GIF was journal impact factor, whatever that is. And so that's going to be our X's. So this column right here, GIFs are X's, and the Y's are the costs. So X is here, Y is here. So I'm going to go over here to Stat, and calculator, hit Stat and Edit. I'm going to go to List 1 and clear it, and List 2 and clear it, which is already cleared. And I'm going to put my X's in List 1, 3.139, 2.943, 2.386, 2.325, and 2.115. In List 2, being sure to line them up where they match, I'm going to put the Y's, which are the costs. $465, $624, $499, $90, and $699. Okay, so now we have X's and Y's, our ordered pairs, in a table there, basically, in our Stat Edit. Actually in our list. L1 is the X list, L2 is the Y list, and they are lined up, so the first one is the ordered pair. Okay. So we want to do a linear regression with this. First thing I might want to do is to graph it. So make sure there's nothing else turned on. I'm going to Stat Plot, second Stat Plot. Go to number 1, turn it on, make it a scatter plot. X's are in List 1, Y's are in List 2, and mark it with the little square. So we want it to set up like this, and quit. And I'm going to do a Zoom 9, and Zoom 9 is Zoom Stat. I'll show you. I happen to remember it's 9, but if not, if you don't remember, just go on down till you find Zoom Stat. And this is going to graph the data so that I can see all of these ordered pairs. It should. Let's go back. Did I not have something set up wrong in the stat plot? Let's go back and see. List 1 for X's, List 2 for Y's. Oh. Turn it on. Maybe it wasn't turned on. Okay, now do Zoom Stat. There we go. There's our data. Doesn't look like a very good, looks like they're very correlated, but we can give, we can go ahead and work this out. So I'm going to go to Stat. We'll quit out of this. Go to Stat, Calculate, and Linear Regression is number 4. And I'm going to do a couple things. I'm going to tell it list 1 is my X list, comma, list 2, my Y list, comma, and I'm going to go to my variables here, go to Y variables, function, and I'm going to put my formula in Y1. So when I hit enter, it's going to tell me what my formula is, and some of this is what I need here, round to the nearest tenth. So the slope is right here, that's the A, and the formula over here. Okay, so that's going to be 49.6, and the constant coefficient, the constant term is 347.3. Now we know a lot about lines, so we know that this line here, this is the y-intercept, and this is the slope. The 49 is the slope. Okay, I'm also going to hit, let me quit for a minute, and go to y equals. Notice it put the values in there. So now if I hit graph, it's going to graph the function with it. Now in this particular case, there's basically no real relationship here, no linear relationship. So this line is a really, really bad fit. One of the measures of this line, of how well it fit, let me redo that calculation. It should give me an R value. Now to get that R value, it's not showing it here. So you only have to do this part once. We go to Catalog, and we go down to Diagnostics. So I'm going to go D, and let's find Diagnostic in here. And turn Diagnostic on, and that turns it on. So now if I do second enter a couple times, now when I pull this back, it gives me an R and an R square value. Your book talks about what the R and the R square value are a little bit more. We're going to talk here about how to interpret them. If you have an R value of 1, that's a perfect linear fit with a positive slope, and an R value of -1 is a perfect linear fit with a negative slope. So notice a positive R here says that this is a slight increase to our line. It's a positive slope, but it's a R value and an R square value that are really close to 0, which indicates there's basically no real linear relationship here. This is a very, very poor fit, and of course you can see that from the graph. Let me just double check and make sure I've got everything typed in right. GIF cost. Okay, everything is typed in correctly. Alright, practical interpretation of the slope. Okay, so remember, slope is delta y over delta x. So that's, in other words, it's how much y goes up when you increase x by 1. So let's see, each additional unit increase in journal impact factor, increasing x by 1, the mean cost of the journal, okay, is estimated to increase by $49.6. Okay. However, that is a very weak relationship. Okay, let's try this next one. Cost to number of citations. Cost is y this time. Okay, hang on a minute. I'm just to look ahead here. Okay, and each one of these costs is y, so we're just going to be changing what the x's are. So I'm going to go back to here, go Stat, Edit, and I'm replacing the Y's are going to be left alone. I'm going to change what's in the X list. So this time I'm doing number of citations. Okay. So there did not appear to be any kind of real relationship between this GIF and the cost. Let's look at the number of citations. This might be a stronger relationship. And we definitely have a problem here because these should have the same number of things here. Type something in wrong. Let's see. 207, 541. I got 2 of the 249s. Let's delete one of those. Alright, they're in there correctly. Since I've already set up my stat plot the way I need it here, all I really have to do is do zoom 9 and it will graph it. Okay, that's at least a little more relationship that seems better, although this does look like it maybe goes up and comes back down. Looks like a quadratic might be a better fit, but a linear relationship may be at least more reasonable here. Let's go ahead and calculate what that would be. Again, we go to Stat, Calc, number 4, List 1, List 2 for X and Y list, and I'm going to do it this way to get Y1. And this will replace my Y1 I had in there before. And this time, since I have my diagnostics on, we get this, so a much bigger R. Still not a great fit. R is only 0.72. R squared is only 0.5, so that's not a very strong fit, but better. Okay, round to the nearest tenth. The slope is over there, it's A, so it's 1.1. And the y-intercept of this one is 129.2. Okay, and a practical meaning of this, each unit increase to the number of citation, the mean cost is, again, this is positive, so it's increasing. If it had been negative slope, it would have been decreasing. And by $1.1. $1.12 if you round to the nearest cent. Okay, do the same thing cost and RPI. Okay, so redo our data, edit. Cost is still Y, so I don't have to change that column. Clear out list 1 and do RPI. 1.17, 0.77, 1.11, 0.3, 0.93. Okay, just double checking my data. Anytime you're entering data, you want to double check and make sure you've typed it in right. Okay, and again, actually if I just do second entry, that will put it there, and now we have a R not as strong as last time. But if I do a zoom 9, I skipped this on the last one, should have shown you this. There's our line of best fit there. Let's see. What do we get here? So the slope this time is A, 455.1, and the y-intercept is 85.8. For each additional increase in the relative price index, the mean cost is estimated to, again, it's positive, so it increases $455.1. Next question. Suppose that you are interested in determining the cost of tuition and fees at universities in the United States, and suppose that we unrealistically know that the standard deviation in all tuition costs is $1,000 per semester. You decide to take a sample and determine a 90% confidence interval for the mean cost, and you want your estimate to be accurate within $500. What's the minimum sample size needed to construct this confidence interval? Now this is going to give first of all, we know sigma, so we're dealing with, and we're talking about finding a confidence interval for a mean. So we're talking about a z-interval. The confidence interval goes from x bar minus the error up to x bar plus the error. So for a confidence interval for a mean, it's centered up on the sample mean. Now, what is the error? The error, if you remember how we found this, we took our confidence level is 1 minus alpha, okay, and that's essentially going to be a region right in here of 1 minus alpha. So our alpha is split up here as alpha over 2 and alpha over 2 here. Okay, so we basically do, well, that area all the way to there is 1 minus alpha over 2. So we basically do an inverse normal of 1 minus alpha over 2. That'll find what the book calls, that'll find this z value, what the book calls z sub alpha over 2. That's what it's usually called. Alpha over 2 is to the right here. The area to the left, though, is 1 minus alpha over 2. So that inverse normal will give you that. And then that will tell you how many standard deviations you are above the mean. So we have to multiply this by the standard deviation of our thing, which is our sigma for all the x's, but we're dividing by the square root of the sample size. So you use this formula in this form to find the error, solve for n, and we see n is inverse normal 1 minus alpha over 2 times sigma over e, and then square the whole thing. So we're going to use this formula in our particular case here. Okay, we know sigma is 1,000. 500 is our error. So 500 is the error. Sigma is 1,000. And this is an inverse norm. Okay. The 1 minus alpha over 2 is 0.9, I believe, in this case, wasn't it? 90%? So if it's 90%, that means that alpha, 1 minus alpha is not 0.9. So that means alpha is 0.1, alpha over 2 is 0.05, and 1 minus alpha over 2 is 0.95. And it's the 0.95 that we put in here. So that's n. Always round up on n. So let's do that on the calculator. Parentheses, inverse normal, that's distribution, and that's number 3. And you just put in the area to the left, 0.95 times 1,000, and then divide by 500, and then square the whole thing. About 10.8, 10.822, so you'll round up to 11. Even if this had been 10.1, we would round up to 11. Okay, because if we get just a little bit bigger sample size, and that's just going to either give us a little bit better higher confidence level or a little bit better smaller interval. We can live with either one, but what we can't get as good if we don't get this big. So we need 11 for this. So round, and it reminds you, round up to a whole number. The recommended amount of sleep is 8 hours per night. A sample of 10 randomly selected college students was taken and found to have the following number of hours of sleep. Okay, I've got some data. I'm going to type this in. So I'm going to go to Stat Edit. Let me go ahead and just clear out these lists that I was using earlier. You know what? By the way, while I'm at it, let me clear that and turn off my stat plot. Should always do that when you finish a stat plot of any kind. Okay. So what we're going to do now is put this in our data. So stat, edit, put our data in our calculator. 5.2, 6.8, 6.2, 5.5, 7.8, 5.8, 7.1, 8.1, 6.9, and 5.6. Okay, let me check them all again just to be sure I got everything in right. Okay, it looks like to me I've got them all in. Now, it says compute the mean and standard deviation, and then it wants a 95% confidence interval for the mean. It's actually going to compute those when I compute the confidence interval, so I'm just going to let it do everything for me here. Notice we don't know anything about the population standard deviation, and we're doing a confidence interval for the mean. Confidence interval for mean makes it z interval or t interval. So one sample, so it's just a one sample z or one sample t. But we don't know the population standard deviation, and definitely it's a small sample, so we're going to be using a t interval. Quit, stat, go to test, and a one sample t interval, I believe is number 8. Let's look here and see. 8, a t interval. We're going to do it from data, so we go over to here and hit enter. Our data is in list 1, that's where I put it, with frequencies of 1. Confidence level is 95%, so it's 0.95. And we go here and calculate, and it's going to do this and go, hopefully we have 3 decimal places in our answer, so we don't have to do it the other way. 5.787 and 7.213 is our confidence interval. So we're 95% confident that the true mean is somewhere in that interval. What was the mean that we actually got, of course, is 6.5, which is exactly right in the middle of that. And the standard deviation we got is 0.9967. Now, that's the confidence intervals. Now suppose we want to perform a hypothesis test that the students at this college average less than 7 hours. Less than indicates a left-tailed test for alternative hypothesis. So the null hypothesis is that the mean amount of sleep is 8 hours. That's what they claim, so we're going to believe them unless we have evidence to otherwise. Okay, so what kind of test statistic? That's a t-test, and then we have a p-value, and this one, then the conclusion, this one we don't have to find the critical values. So luckily that's exactly what a t-test gives us on the computer, the calculator here. So we go stat, go over to test, and a t-test is number 2. We're doing it from our data, and the hypothesized mean is 8. And list 1's where our data is, and we're doing a left-tailed test. We want to test that the true mean is less than the 8 that they say, and we're going to calculate that. We could also have it draw it for us on the t distribution. What is the test statistic? That's a t-star, which is right here. That's negative 4.7593, 4 decimal places. And what's the p-value? Well, don't forget this e negative 4 at the end. That means 10 times 10 to the negative 4. So move the decimal 4 places to the left. That is 0.123 zeros, and then the fourth place is actually a 5, and that's where we're rounding off to. Well, that's a very small p-value, so we know at any reasonable alpha we're going to be rejecting, and in fact at an alpha is 0.1 we'll certainly reject. That p-value is less than alpha. So is there enough evidence to determine that college students at this one average less than 7 hours of sleep per night? That is a yes. In my case, college professors are going to get less than 7 tonight too, because it's already almost 11 and I'm going to be at this a little while. Alright, next.